fine.
I'll take that as the yes. One. A bunch of folks have touched on before, but this is, I figured I'd take this chance to sort of disseminate some of what's been going on with the work that Dr. Ting and I have collaborated on, and some different ideas about how to approach this sort of recurring problem for Forth in the modern age. Being able to run Forth in general on top of C is sort of a top of mind thing for a lot of folks. As there was an interesting discussion actually that happened in the email thread prior to this, and I'll try to touch on some of those points. But it sort of provokes the question of why C, and sort of the motivation, as I mentioned in that email, is that there's in the modern world, you want to interface with the operating system. Oftentimes, operating systems have gotten big and are not getting any smaller. There's a lot of code out there. Some of it is very large and complex, but some of it is useful and a thing that I think that depending on what you're trying to do, you can benefit a lot from. Modern architectures have gotten more complicated, although as I'll discuss later, I'm not sure that warrants necessarily jumping in and moving to a C-based Forth. Some of it is because of the tools. It's and we'll talk about this a little bit later, but it's gotten pretty hard to live in a world where you're sort of making your stone knives and whatnot from scratch. So, and some of this is also motivated by fighting the complexity of the tool chain and the operating system ecosystem and all the things around you with sort of its own tools. So, but backing up a second, why C in particular? I'm getting a little echo. Why C in particular? So the canonical example is it's sort of a portable assembler. There's a lot of architectures. You can kind of get one big win. You do it once, and in principle, it's portable. There's a degree to which that's not true, and we'll talk about that later. But basically, it's also the basis for almost all operating system ABIs. The interface to the OSs are sort of heavily built on it. And even outside of the operating system space, there's a lot of substantive libraries, sort of the ones that do the low-level things that you might actually want to do with the kinds of projects folks do with Forth. There are some other options. Rust is gradually sort of getting all the pieces that you might need to do interesting things. I'm seeing a thing on the chat, which I will need to get on a separate window if I can manage to. No, that's not doing the thing I want to do. I'm gonna, for reasons I don't understand, this is not showing. Oh, I see. Can I get it over here maybe? I'm gonna not get derailed by that. But feel free to chime in with questions verbally. I'm having trouble seeing the chat simultaneously. So there are some other options of sort of low-level languages that have come into their own a little bit. But fundamentally, I think the problem is that they're still built on top of the tool chains that have been built out for C, and stacks like the GCC tool chain or LLVM right underneath. And so it's sort of maybe, but not today, so to speak. So let's talk about some of those. Interfacing with the operating system is a big one. I myself live in a sort of a multi-OS situation at work. I'm on frequently sort of between different operating systems. A Mac laptop, but remotely connected to lots of Linux machines, debugging an Android device with something that's vaguely Linux-like. At home, I'm on Windows devices or Linux devices, and sort of a mixture. And I literally have some of them strewn through my house and whatever I happen to pick up. Sometimes I'll tinker with a Raspberry Pi. Sometimes I'll tinker with various embedded boards. And so, and each of these has something that resembles vaguely an operating system on them, and I aspire to ignore them, but oftentimes you want to interact with them. So, and they do lots of complicated things. They have graphics drivers that if you want to actually interact with the graphics system, you have to do you have to sort of talk to them. In some cases, it's even proprietary drivers. It's similar with a network stack, or if you want to interact with other applications, or if you want to interact with the wider internet and all of its protocols. There's a lot of complexity, and if you can sort of weave all of that, you can try to weave all of that from scratch, but being able to bridge that divide is important. And even little things like the executables have gotten sort of more complex. That now have to support a range of architectures. There's I mean, this has been the case for some time, but like there's the sort of slow evolution of how simple things like stick an icon inside of an exe have continued to be fraught. And they have complicated calling conventions. There's sort of how you do it on Linux or how you do it on Windows, and these are all details that you can to some extent wrap up and bundle up and not have to sort of think about at least as deeply if you're sort of leveraging C. And then they pass around complicated data structures, right? Like if you want to interact with X windows, you've got to interact with these particular layouts of data and memory, and you can meticulously replicate each of them yourself. But in many cases, especially on the sort of Unix-derived platforms, the interface itself is sort of prescribed as being the header file, and the assumption is that you can rebuild everything from source, and there's an implicit assumption that source is C source code. And even worse yet, this is even present on the embedded devices like ESP32. You want to use one of the Wi-Fi libraries, and the wrinkle of dynamic linking, right? Like oftentimes you'll get bootstrapped in some kind of an interesting small forth, and then you want to interface it to the outside world. And one of the paths there is you could use DL Open or equivalents on Windows and try to reach out into the world and interact with it. And it's nice to have things like what GForth gives you, where you can pull in individual C functions. But where it gets kind of grisly underneath is that when you actually start interacting with data structures, oftentimes you're back sort of embedding little snippets of C code in your program to make it work. Because you need to know something about a structure layout that's particular. Okay, too many of those. There's the code that you can generate, and that's gotten a little bit more complicated. I mean, in the intervening, architectures don't do what they say on the tin anymore. They used to be, you could look at timings and the instruction set and whatnot. That's an abstraction now on top of something else. The instruction set that you feed into an x86, something else comes out the other side, and there are all kinds of considerations in terms of like how how that transformation occurs, and to some extent that knowledge is embedded in compilers. Now, in all fairness, the compilers that are out there kind of weave in and out of sort of the particulars of this, and the degree to which they've really baked in knowledge of this sort of complicated optimization space is sort of subject to debate. But at the very least, they get the basics. They know things like, oh, the code cache is going to load a whole 16-byte chunk of the instruction set and convert that to the actual underlying microarchitecture, or you're going to freak out the floating point unit if you change the bounds in the stack, or you've got sort of the right symbiop to do in place of a thing you might have done previously a different way. And just to illustrate this, like, for those of you who have heard of the Spectre attack, like there's so much complexity in the systems that we're running on top of now that just the hum and noise of them can be used as a side channel to extract information about what else is going on in the system. So there's, sort of, it's not quite what it once was. One illustration, talking about this, I'm going to talk about the block boundary one just as another example, because it'll show up in some of the machine code snippets I'm going to show in a second. But simple thing like a no-op, doing nothing on contemporary systems. There's more than one way to do it. There's a NOP of every byte length, because when you're converting to the microarchitecture underneath, if you have a bunch of individual NOPs that are in a row, those are going to each turn into one micro-op. But if you have one of these fat NOPs, those will get converted to something that converts into a single instruction in this hidden instruction set that varies between between versions of a chip and the ones you can see and can't see. And why would you care? It's because you're loading 16, when you access one of them, you're actually loading 16 bytes of them at a time. So if you're, trying to get all the performance, you're going to care about these things. There's also, because you're trapped by the tools, we can't even agree on one syntax for assemblers, and which ones are available for which devices is still a surprisingly disparate problem. One that I think motivated a bunch of the things that sort of drove Dr. Tame to think about EForth on top of C is ESP32. There is a tool chain, and it's a 700 megabyte tool chain that has its own libc and its own RTOS and a Wi-Fi stack and BLE. And you can theoretically, there's a copy of it you can use on Windows, but if you're trying to do anything sort of that requires tip of trunk changes, you're going to have Linux or the Windows subsystem for Linux, and build it tip of trunk and interact with it directly. Arduino wraps this up really nicely, and if we're trying to engage with a wider community of folks, having a version of a forth that you can have in one file that you can load into the Arduino IDE that sort of handles the problem of package management, hides all of the complexity in the manufacturer's toolchain is great. And then there's the challenge of converting resources. I'm going to move on. So anyways, let's assume you're sold in this. How to do it? A couple of different approaches are out there. Individual words as functions, token threading, or computed goto, or a hybrid of these. I'm going to breeze through this because I'm noting the time. So let's look at words as a function. The idea is you put each core word into its own function. You can use a function pointer to it. You have a tight loop like this that goes through and builds up or goes through and executes them one by one. The problem, of course, is that this, then you get something like that for add and something like that for the main loop, and it's actually quite a lot of cycles to do. This is, however, close to what some of the EForth ports out there are doing underneath. I'm going to introduce X macros. I want to disseminate this more widely for those of you who are doing C and haven't seen this trick. So X macros are the idea of using the C preprocessor to build up a list of code, and it lets you do some interesting things. So you could define a pound define, and you want to use slashes, to separate things into multiple lines. A list like this, where you've got a table of like string names and identifiers and chunks of code, and you can use this to build up a table describing sort of all of your core words in your forth. And then when, for example, you want to be able to say, come up with a single unique identifier for each of them, you can define a wrapper that like this that will pull out the relevant fields, build up a single line, and then will generate each of the things in your list. So you get each of these splayed out in this spot within the code. And this comes up with a number of C-based forths. You want to have sort of all of my core words. I'm going to do something with them, build them up in the dictionary, come up with an ID for them, that type of thing. And then you can use them over and over again. So this is sort of a structure you'll see. You can do a token threaded forth with a core like this, but one thing you'll run into is that your individual words will. This is not the. Oh yeah, you'll have dispatch where you'll look up an individual word in a table, do a jump to some handler like this. But it's quite a lot of code, quite a lot of operations that are happening for dispatch, and it's the same whether it's a little bit better on Clang, but not much. Another technique that's highly useful here is to use computed gotos. So the idea is that this is not technically ANSI C, but it is present in Clang, it's present in GCC. If you have a label in your C code, you have a certain spot. You can get an address to it. A double ampersand will give you the address of that label. And then you can actually have a goto, and that lets you do something closer to what you would want to do in a traditional forth, because you're now able to do a jump instead of a call in various places. The downside is this all has to be in the same function, so you're going to have some very big functions, but that's what the X macros are for. It lets you build these things up. And then you can build up your definition for next for like an indirect threaded forth or direct threaded forth, and then build up a table of your core words. You can set some things up in a few registers, and to some extent you can try to give hints to the C compiler what registers you want it to use, but it will happily ignore you a lot of the time. So good luck with that if you're trying to use it for a stable interface to the outside world. Better off to use actual calls into C function pointers when you're trying to bridge to the outside. And then you put these in a table, and what you end up with is still not great, at least on GCC. And this speaks to the I think there's a sort of a frequent thing that people will say that, oh, the compiler will do great. It varies, especially when it's code that looks like a forth interpreter or just any interpreter at all. It tends to be an edge case that's handled very poorly in contemporary compilers. And the folks that work on GForth are regularly harassing the GCC folks because they have a regression that makes their computed go-to code turn into something inefficient in GCC. So this works out a little bit better in Clang. You get a single landing point for your indirect implementation of and the same thing for direct thread. This is about as tight as you could do for an an add operation by hand. There's the memory model, which I'm a little over. Kevin, I don't want to bust your schedule. I got a handful more. Shall I?
Go for it.
Go for it. All right. Memory model. This is a problem. OS memory is big and full of places that you can fault. A traditional system, there were lots of places in memory, but if you poked the very bad one that touched your I/O controller, something bad would happen. Now most of memory is filled with unmapped pages, and you're going to page fault on a contemporary OS. So there's questions about how you deal with this. Your code might have to be relocatable. The OS might move you around for security. A few different approaches that folks take. They'll the EForth approach, at least the conventional one, is to have a small 16-bit area that you operate in, and then some explicit operation like peek or poke to talk to the outside. WinForth works around the issue of a base by having this sitting constantly in a register, but you're paying a continual performance cost for this. GForth does possibly the simplest and most straightforward thing, which is just install a signal handler, intercept the error, but that's a lot more work and a lot more hassle to make that work nicely. How do you bootstrap the dictionary? Lots of different options. You can try to do it in Forth, but the challenge is which one, and especially if you're having to sort of connect this with a Forth in C, that you're really then just using Forth to generate code, which is oftentimes a pain, or at the very least generate a table. Dr. King has iterated on some different variations of this. I've done the same. I've done it in JavaScript even for some Forths. Doing it with X macros can be nice. You can sort of just build it up directly in the code. If you have the strings, you can have an X macro generate some code that sort of at startup builds up the dictionary. That's certainly one approach. And then you deal with things like immediate words by having sort of a separate macro for them and drive them through. What Dr. Ting's moved to most recently in EForth is kind of cool. He's using variadic functions to have a colon definition, and then is able to do codes like this to build up words, and it actually sort of looks very similar. You can even build in smarts to do your conditionals inline, and you do this with variadic macros. There's a bunch of implementations out there that you can look at. If you look at StenoForth is the one I'm sort of fuddling with recently, that I'm trying to make cross-platform to Windows, Linux, and web via Asm.js. There's a bunch of different branches. If anybody goes looking at ESPForth for the EForth there, I should say StenoForth is somewhat EForth. It's fairly EForth derived. And then there's sort of a bunch of different variations of these. Some have web support, some have background thread support to a limited extent. I'm going to skip over this in the interest of time. In some future presentation, I'll describe this slide deck tool, but that's enough for now. Are there any questions?
A simple one. Do you have a website with all this information?
I have, yes, and I'll share links out to this. Yeah, not quite as sort of cogently laid out as all of that, but I have a collection of places to point folks that are interested to learn more, as well as the slide deck and all of that.
Have you looked at how, particularly on an x86, the different architectures end up operating with the caches? Because the caches are quite large and very fast.
It is a fair point. You know, especially the size of your typical Forth program. Oftentimes, you can live in cache, and a lot of these issues kind of melt away naturally. It depends a little on what you're doing. I would say that some of the yeah, I mean, it's you know, the behavior of the caches is yet another thing to take into account, and the data cache, if anything, is, I think, more of an issue for the situations that I've dealt with. Typically with Forth programs, at least of the scope that I'm writing, they're small enough that I probably don't need to be worried about every last iota of efficiency in terms of getting the code into the microcache. Once it's there, into microops, but once it's there, you know, each op you can save at least buys you something. So yeah, I don't know if that, but yeah, the data cache, huge issue, and the order you touch, especially if you're doing image manipulation, you know, every little twist of how you touch the data influences how fast things will be.
So Brad, I'd like to encourage you to expand on this in a future talk, maybe January or February. I'd also like to comment that everybody is encouraged, the speakers are encouraged to send their slide decks and other material on to Dave Jaffe, who will put it on the SVFig web archive of such things. If you have a past talk that you want to see the slides from, likely as not, they are there. Thank you, Dave. I'd like to move on at this time unless somebody really has something desperate that they need to say. Okay, then. I assume that Mitch Bradley is on deck. If you're not muted, I'm going to mute Joe since he just got up. If you're not muted, don't make me have to mute you. Please mute yourself if you're not the presenter. Hello, Mitch Bradley. Mitch Bradley, hello. All right, Mitch Bradley, who is a no ne'er-do-well, seems to be absent from our company at this time. We're currently at 39 participants, which is a jolly nice number in my opinion. Let me just take a quick look. Well, that's a confusing thing. All right, so Don Golding. Don Golding is okay. I don't see Don in the list of participants either.
You threw everyone off with the early morning time. Everybody got used to the afternoon.
Oh, I sent them all notes that said, okay, this is the agenda and here's the link and all that stuff. So both of Don's talks are off the table at this time. I'm sorry I stepped in to curtate your talk, Brad. And I assume that Bill Ragsdale is ready because he's always ready. Bill?
I'm ready. It'll take about 3 clicks to kind of click over, so hold on. Talk among yourselves.
Okay. So.
But we're all muted.
Yes, okay. you can unmute to talk among yourselves. I'm wondering why we don't have mute upon entry, but I guess if you're new to this, you don't want to just start off being switched off.
It's a setting in your Zoom that you
No,
can
I
have the
could
vid-
I could do it. I'm just musing to myself why we haven't.
Hi everybody. I'm joining from Berlin. Sorry, I was working on something, so I couldn't follow the discussion so far. I had a project. Can we like demo in the force in this session? Like, I mean,
I tell you what, if you can wait till lunchtime, there'll be sort of a random access virtual chat. We have an agenda that we're trying to get through.
Yes.
And I expect that lunch will be expanded since a couple of the speakers informally bowed out. So wait till noon and introduce yourself at that time and show your stuff.
Sure.
And you're welcome at future sessions. Send me an email, forther@comcast.net. And I'll get you on the list. If you can message me through Meetup, you won't even have to remember my email address.
Yes. I was wondering if. Okay. That's actually. I was actually wondering who canceled their talks.
Well, they canceled them by not showing up.
Okay.
So there are two people
I was wondering about
that were
matrix
on the
forms.
agenda.
Like,
I don't know where they are this morning.
yeah. Okay, thanks.
They're both in, I think,